Right now, somewhere in our galaxy, a black hole is pulling a star toward it from thousands of kilometers away. The star doesn't know it yet, but it's caught in an invisible grip, being dragged closer and closer to a boundary it can never return from. That boundary, the event horizon, is so powerful that once you cross it, even light itself cannot escape. Photons, the fastest things in existence, get trapped forever inside. But wait, think about what that actually means. Light cannot get out. Nothing can get out. The event horizon is an absolute prison from which no escape is possible. So here's the problem that's been bothering physicists for decades. If nothing can escape from inside a black hole, not even light moving at maximum speed, then how is the black hole's gravity reaching outward to pull that distant star? How is gravitational force getting out when light cannot? What makes gravity special? For years, this seemed like an impossible contradiction, a glitch in our understanding of physics, but the real answer is far more mind-bending than a simple escape mechanism. Gravity isn't escaping at all, and understanding why reveals what gravity truly is at the deepest level. Chapter 1. Gravity's True Nature. For over 2 centuries, from 1687, when Isaac Newton published his laws of motion and universal gravitation, until 1915, when Einstein completed General Relativity, humanity understood gravity as a force. Newton described it mathematically with elegant simplicity. Every mass attracts every other mass with a force proportional to the product of their masses and inversely proportional to the square of the distance between them. This formula worked brilliantly, predicting planetary orbits, explaining tides, allowing calculations of everything from falling apples to the trajectories of comets. But Newton himself was deeply troubled by one aspect of his theory. Gravity in his framework acted instantaneously across any distance. If the sun suddenly vanished, Earth would immediately fly off in a straight line, deviating from its orbit at the exact instant the sun disappeared, even though the sun is 8 light minutes away. This instantaneous action at a distance seemed almost magical, requiring no medium or mechanism. Newton wrote in his Principia that he feigned no hypotheses about how gravity actually worked, only that his mathematical description matched observations. The problem festered for centuries. How could gravity transmit influence instantaneously across empty space? What was the mechanism? Newton's theory provided no answer, only accurate predictions. Then in 1905 and 1915, Albert Einstein revolutionized physics twice. First with special relativity, showing that nothing can travel faster than light, then with general relativity, revealing what gravity actually is. Einstein's insight began with a thought experiment he later called the happiest thought of my life. In 1907, sitting in his patent office in Bern, Switzerland, he imagined a person falling from a roof. During the fall, the person would feel weightless, unable to distinguish their situation from floating in empty space far from any gravitating body. This simple observation that freely falling motion eliminates the sensation of gravity revealed something profound. Gravity and acceleration are equivalent. Let me establish this equivalence clearly because it's the foundation of everything that follows. Imagine you're inside a closed room with no windows. Someone asks you to determine whether you're sitting still on Earth's surface, experiencing gravity, or accelerating upward through space at 9.8 meters per second squared with no gravity present. According to Einstein, there is no experiment you can perform inside that room to distinguish between these situations. They are physically equivalent. Gravity pulling you downward and acceleration pushing you upward create identical physical effects. This equivalence principle led Einstein to a radical conclusion. If gravity and acceleration are indistinguishable, and acceleration is just motion through spacetime, then gravity must also be motion through spacetime. Gravity is not a force pulling objects together. It's the natural motion of objects through curved spacetime, following the straightest possible paths through geometry that has been warped by the presence of mass and energy. To put this in perspective using a metaphor that captures the geometric nature, imagine space-time as a stretched rubber sheet. Place a heavy ball in the center and it creates a depression, curving the sheet. Now roll a smaller ball across the sheet. It doesn't travel in a straight line. It curves toward the heavy ball, not because the heavy ball is exerting a force on it, but because the geometry of the sheet itself has been curved. The smaller ball is actually following the straightest possible path through curved geometry. This is what gravity is. Mass and energy curve space-time, and objects move along the straightest possible paths called geodesics through that curved geometry. When you throw a ball, it follows a parabolic arc, not because Earth's gravity is pulling it downward, but because Earth's mass has curved space-time in such a way that the straightest possible path through that geometry is a parabola. When Earth orbits the Sun, it's not being pulled by an invisible force. It's following a straight line through curved space-time, and that straight line through curved space appears as an elliptical orbit when viewed from our perspective. Dr. Brian Greene at Columbia University describes this transformation as the most beautiful idea in physics. Newton told us what gravity does, providing mathematical formulas for its effects. Einstein told us what gravity is, revealing it as space-time curvature rather than a force. This distinction is not mere philosophical preference. It makes different predictions, and observations confirm Einstein was right. The first confirmation came in 1919 during a solar eclipse. Arthur Eddington led expeditions to observe starlight passing near the sun's edge during totality. If Newton was correct, starlight should be deflected slightly by the sun's gravitational force. If Einstein was correct, starlight should be deflected by traveling through space-time curved by the sun's mass, and the deflection would be exactly twice Newton's prediction. Eddington's measurements matched Einstein's prediction precisely. Space-time curvature was real. Since then, countless experiments have confirmed general relativity with extraordinary precision. GPS satellites must account for space-time curvature to provide accurate positioning, because time runs slightly faster in orbit than on Earth's surface due to weaker gravitational field. Gravitational lensing, where massive galaxy clusters bend light from distant galaxies behind them, creates multiple images and Einstein rings exactly as predicted by space-time curvature. And most dramatically, gravitational wave detectors have observed ripples in space-time itself propagating from merging black holes and neutron stars, confirming that space-time is a dynamic, flexible medium that can wave and oscillate. But here's what makes this relevant to our central question about black holes. If gravity is space-time curvature rather than a force being transmitted, then asking, how does gravity escape from a black hole, is asking the wrong question. It's like asking, how does the curvature of a bowling ball escape from the bowling ball? The curvature is not inside the ball trying to get out. The curvature is a property of space near the ball, existing wherever the ball's mass influences space-time geometry. Consider what happens when a massive star collapses into a black hole. The star's mass curves space-time around it. As the star contracts, the curvature becomes more extreme, steeper, more tightly curved. When the collapse crosses the point where escape velocity equals light speed, an event horizon forms. But the space-time curvature doesn't suddenly stop at the event horizon. It extends smoothly outward, decreasing with distance according to the same mathematical relationship that describes gravity around any massive object. The black hole's gravity is not emanating from inside the event horizon. It's the geometric property of spacetime in the region surrounding the black hole, including both inside and outside the horizon. Objects outside respond to the curvature in their local region of spacetime. They don't need information from inside the horizon because they're not responding to conditions inside. They're responding to the geometry of their own local spacetime, which happens to be curved due to the mass that formed the black hole. To put this in terms that connect to your intuition, Imagine you're walking on a hill. The slope of the ground under your feet determines which direction you tend to slide. You don't need information from the hilltop to experience the slope where you're standing. The slope exists locally right under your feet as a property of the ground's geometry. Similarly, gravity exists locally as a property of spacetime's geometry. You don't need information from distant masses to experience their gravitational influence, because that influence is encoded in the geometry of your local spacetime. This geometric understanding of gravity explains why it doesn't need to escape from black holes. Light needs to escape because light is composed of photons, particles traveling through spacetime at light speed. When photons try to move outward from inside an event horizon, they're traveling through spacetime curved so severely that all outward paths lead back inward. The photons are trapped by geometry, but gravity is not traveling through spacetime. Gravity is the curvature of spacetime. It's not trying to get out because it was never in. The event horizon is a boundary for things traveling through spacetime, not for the geometry of spacetime itself. Mass curves spacetime, and that curvature extends as far as spacetime extends, unimpeded by event horizons or any other boundary, because the curvature is the boundary, not something that needs to cross it. You might be thinking this seems like semantic wordplay, distinguishing between gravity as a force and gravity as geometry. But the distinction is physically meaningful and observationally confirmed. Forces are transmitted by particles or fields that carry information at finite speed. Geometry is a state of spacetime that exists wherever spacetime exists. This difference explains why gravity behaves differently than electromagnetic radiation at event horizons, and understanding it is essential to grasping what black holes actually are. So gravity is spacetime curvature, not a force, which is why it doesn't need to escape from black holes. But this raises another question: what exactly is light, and why does it get trapped when gravity doesn't? Chapter 3: Collapse Geometry. The formation of a black hole is not an event but a process, a continuous transformation of spacetime geometry that occurs when matter becomes so dense that its own gravity curves spacetime beyond a critical threshold. Understanding this process reveals why the event horizon is not a physical surface or barrier, but an emergent feature of extreme spacetime curvature. Let's start with a massive star at the end of its life. For millions of years, the star has maintained equilibrium between two competing forces: gravity pulling matter inward and thermal pressure from nuclear fusion pushing outward. The star burns hydrogen into helium, then helium into carbon and oxygen, then progressively heavier elements through fusion reactions that release energy. This energy creates pressure that supports the star against gravitational collapse. But fusion has a limit. Iron 56 is the most stable atomic nucleus. Fusing lighter elements into iron releases energy, but fusing iron into heavier elements requires energy input. When a massive star's core becomes primarily iron, fusion ceases. The energy production stops, the outward pressure vanishes, and gravity, which has been waiting patiently for millions of years, wins instantly. The core collapse happens astonishingly fast. In less than a second, a stellar core with more than 3 solar masses of material collapses from about the size of Earth to a region only a few kilometers across. The density increases by factors of trillions. Atomic structure breaks down. Electrons are forced into protons, creating neutrons and releasing neutrinos. The collapse would continue all the way to a point, but the core becomes so dense that neutrons themselves push back, creating what's called neutron degeneracy pressure. For cores below about 2.5 solar masses, this neutron pressure halts the collapse, creating a neutron star, a sphere of nuclear density material about 20 kilometers in diameter. But for more massive cores, even neutron degeneracy pressure cannot stop gravity. The collapse continues through the neutron star phase without pause, and nothing in known physics can halt what happens next. Dr. Roger Penrose, who won the 2020 Nobel Prize for his theoretical work on black holes, proved mathematically in 1965 that once collapse progresses past a certain point, the formation of a singularity becomes inevitable. The matter cannot stop collapsing. It must reach infinite density at a single point, creating what's called a gravitational singularity. This is not speculation or approximation. It's a rigorous mathematical proof within general relativity that singularities must form from sufficiently massive collapse. To put this in perspective using density comparisons, Earth has an average density of about 5,500 kilograms per cubic meter. The Sun averages 1,400 kilograms per cubic meter, less dense than Earth because it's mostly hydrogen and helium. A white dwarf star squeezes about 1 solar mass into Earth-sized volume, giving densities around 1 billion kilograms per cubic meter. A neutron star compresses over 1 solar mass into a sphere 20 kilometers across, reaching densities above 400 trillion kilograms per cubic meter, comparable to cramming all of humanity's mass into a teaspoon. But a black hole's singularity has infinite density, all the mass compressed to a point with zero volume. This seems physically absurd, and most physicists believe it indicates that general relativity breaks down at these extremes, requiring quantum gravity to fully describe what happens. But within classical general relativity, the singularity is an unavoidable consequence of the mathematics. Now let's examine what happens to spacetime during this collapse. Before collapse, the star's mass creates moderate spacetime curvature, extending outward in all directions. As the core contracts, the curvature becomes steeper, more tightly focused. At the star's surface, spacetime curves more sharply than it did when the star was larger. This increased curvature represents stronger gravitational field in the Newtonian language. But it's more accurate to say the geometry has become more dramatically warped. As collapse continues, there comes a critical moment when a surface forms at a specific radius around the collapsing matter, defined by a simple relationship. The escape velocity at that radius equals the speed of light. This is the event horizon. Its radius, called the Schwarzschild radius after Carl Schwarzschild, who calculated it in 1916, depends only on the mass. R spam 2gm(c)2, where g is the gravitational constant, m is mass, and c is light speed. For a mass equal to our Sun, the Schwarzschild radius is about 3 kilometers. For Earth's mass, it's about 9 millimeters. For a supermassive black hole, like the one in M87, with 6.5 billion solar masses, the Schwarzschild radius is about 120 billion kilometers, roughly the size of our solar system out to Neptune's orbit. The relationship is direct and simple. Double the mass, double the radius. Here's what's crucial to understand. The event horizon forms before the collapsing matter reaches it. As the stellar core contracts, the event horizon expands outward from the center. At some instant during collapse, the horizon radius equals the radius of the collapsing matter's surface. At that moment, the event horizon forms and the black hole comes into existence. The matter continues falling inward toward the singularity, but the event horizon remains at the Schwarzschild radius, unchanging. Consider the geometry more carefully. The event horizon is not made of matter. It's not a physical membrane or surface. It's a location in space-time where the geometry changes character, where escape becomes impossible. You could place a detector at the Schwarzschild radius before the collapse happens, and you wouldn't detect anything special when the horizon forms there. No physical wave or field passes through the detector. The local space-time simply reaches the critical curvature level where light cones tip over, pointing all future directed paths inward. Dr. Kip Thorne uses the metaphor of a waterfall to explain event horizon geometry. Imagine space-time flowing like water toward the black hole. Far from the hole, the flow is slow and gentle. Closer in, it accelerates. At the event horizon, space-time is flowing inward at exactly light speed. Inside the horizon, it flows faster than light speed. A photon trying to swim upstream against this flow makes no progress if it's at the horizon and moves backward if it's inside, swept inexorably toward the singularity. This is not actual motion of space-time, which would violate relativity. It's a metaphor for how the geometry is structured, how the light cones are tilted. But it captures an important truth. The event horizon is defined by space-time geometry, not by any matter or energy. The horizon exists because the curvature has reached a critical value, and curvature is determined by the distribution of mass and energy, but the horizon itself is a geometric feature of empty space-time. The 2015 first detection of gravitational waves from merging black holes by LIGO provided extraordinary confirmation of this geometric picture. The gravitational waves were produced by two black holes, each about 30 solar masses, orbiting each other and spiraling inward until they merged into a single black hole. During the final fraction of a second before merger, the black holes were orbiting each other hundreds of times per second, their event horizons nearly touching the space-time between them, vibrating so violently it produced ripples that propagated across the universe. The gravitational wave signal matched theoretical predictions from General Relativity with stunning precision, confirming that black holes behave exactly as Einstein's equations predict. The final merged black hole settled into a stable configuration with an event horizon determined by its total mass, angular momentum, and electric charge. The event horizon formed smoothly during merger, maintaining its geometric character as a surface of no return rather than a physical boundary. To put this in terms that connect to observable reality, consider what happens to matter falling into a black hole from an outside observer's perspective. As the matter approaches the event horizon, it appears to slow down due to time dilation effects. Light from the falling matter is progressively redshifted as it climbs out of deeper gravitational wells. The matter appears to freeze just outside the horizon, taking infinite time to actually cross it from the external viewpoint. Meanwhile, from the matter's own perspective, it crosses the horizon in finite proper time, experiencing nothing special at the crossing, then continues falling toward the singularity. This time dilation effect means that from an external observer's perspective, the collapsing stellar core never quite reaches the Schwarzschild radius. It appears frozen in place just outside, taking infinite external time to cross the horizon. Yet the event horizon still forms and the black hole still exists because the geometric structure of space-time has reached the critical configuration. The horizon is where it mathematically should be based on the mass distribution, even though the matter appears frozen just outside from the external perspective. You might be wondering how a horizon can exist before matter crosses it. This seems paradoxical, but it's resolved by understanding that the horizon location is determined by the mass distribution and space-time geometry, not by whether matter has physically touched some surface. The geometry becomes critical when enough mass compresses within the Schwarzschild radius, creating the curvature level that defines a horizon. The matter is inevitably inside its own horizon once collapse progresses past that point, regardless of what external observers see. So black holes form through gravitational collapse when matter reaches densities that create critical space-time curvature, producing event horizons that are geometric features rather than physical surfaces. But if the horizon is just geometry, just critical curvature, how does it trap light so absolutely while gravity extends beyond it? Chapter 4. Geometric imprisonment. The key to understanding why light is trapped while gravity extends beyond the event horizon lies in grasping what trapped means in curved space-time. Trapping is not about forces preventing escape. It's about geometry eliminating escape paths. Inside an event horizon, there are literally no paths through space-time that lead outward. All possible futures point toward the singularity. Let's establish this geometric picture precisely. In flat space-time, far from any massive objects, you can draw a light cone at any point showing all possible directions light could travel from that point into the future. The cone has a specific angle, 45 degrees if you plot time vertically and one spatial dimension horizontally, because light always travels at constant speed. Anything moving slower than light has a world line that stays inside this cone. Only light itself travels on the cone's surface. When space-time curves near a massive object, these light cones tilt. Near Earth, they tilt very slightly toward Earth's center. The effect is tiny but measurable. The GPS system must account for this tilting because satellite clocks run at different rates than ground clocks due to the different light cone geometries at different gravitational potentials. Near a neutron star, the tilting is dramatic. Light cones point noticeably toward the star's center. At the event horizon of a black hole, the light cones tilt to exactly 45 degrees relative to the horizon surface. One edge of the cone points outward along the horizon, neither escaping nor falling in. The other edge points inward. The entire interior of the cone, representing all possible future paths for anything at that location, points either along the horizon or inward. There are no outward, future-directed paths. Escape is not difficult, it's geometrically impossible. Dr. Leonard Susskind at Stanford describes this as the moment physics becomes unavoidable fate. Outside the horizon, you can choose to fall in or escape, expending energy to follow different paths. At the horizon, your choice is narrowed to one dimension, along or inward. Inside the horizon, even that choice disappears. All paths lead to the singularity, which is not a location in space, but an instant in your future when space-time curvature becomes infinite. To put this in perspective using a metaphor that captures the geometric constraint, imagine you're on a river approaching a waterfall. Far upstream, you can row in any direction, including back upstream against the current. Closer to the waterfall, rowing upstream becomes harder, requiring more energy. At a certain point, the current equals your maximum rowing speed. Beyond that point, the critical line, you cannot row back upstream no matter how hard you try. That line is analogous to the event horizon. Once you cross it, all your possible futures involve going over the waterfall. But here's the crucial difference between this metaphor and actual event horizons. In the river, you're fighting against water flow, a physical force. At an event horizon, there's no force fighting against you. The geometry of space-time itself has reached a configuration where outward directions simply don't exist in your future. The light cones have tilted so far that every direction you can point, every path you can take forward in time, leads inward. Now let's examine how photons experience this geometry. A photon always travels on the surface of the light cone, moving at exactly light speed. Far from a black hole, a photon emitted radially outward travels away from the black hole, moving through progressively less curved space-time as it climbs out of the gravitational well. It's redshifted in the process, losing energy, but it escapes successfully. As the emission point gets closer to the event horizon, the outward-directed photon struggles more. The light cone is tilted more severely inward. The photon still travels on the cone's surface, but that surface points more and more steeply. A photon emitted at the event horizon aimed directly outward travels along the horizon itself, neither escaping nor falling inward. It's frozen geometrically, hovering at the critical radius. A photon emitted inside the horizon finds that even the outward edge of its light cone points inward. There is no outward direction to aim. Every direction, what we would call outward, inward, or tangent in flat space, all lead deeper into the black hole when you're inside the horizon. The photon hasn't changed, it still travels at light speed. The light cones, the structure of possible motion through space-time, have changed so dramatically that all motions lead inward. The 2020 simulations by the Event Horizon Telescope team visualized this effect beautifully. They modeled photon trajectories near the supermassive black hole in M87, showing how light from hot gas swirling around the hole follows curved paths through warped space-time. Photons emitted outside the photon sphere can escape, but their paths are bent, creating the bright ring visible in the image. Photons emitted inside the photon sphere spiral inward, some completing several orbits before falling in, creating a complex shadow region larger than the event horizon itself. Dr. Ferial Ozel at the University of Arizona, part of the EHT collaboration, describes the shadow as watching geometry in action. Every photon trajectory is determined purely by space-time curvature. No forces act on the photons. They simply follow straight lines through curved space-time, and those straight lines twist into spirals, circles, and inward plunges based on the local geometry. The darkness of the shadow is literal absence of photons, a region where geometry prevents any light from reaching observers outside. Consider what this means for the difference between gravity and light. Photons are entities moving through space-time, following geodesics determined by local geometry. They can be trapped when geometry becomes so curved that geodesics lead only inward. But gravity itself is that geometry. It's not something moving through space-time that could be trapped by space-time. It is the shape of space-time. When we say gravity extends from a black hole, we're really saying that space-time throughout the region surrounding the black hole is curved in a pattern determined by the black hole's mass. This curvature exists everywhere simultaneously. It doesn't propagate from the black hole outward. It's a property of space-time that was established when the black hole formed, or more precisely, when the matter that became the black hole was in place. To put this in terms that highlight the geometric nature, imagine a landscape with hills and valleys. The shape of the landscape is geometry, describing how the surface curves. Now imagine rolling a ball across this landscape. The ball follows a path determined by the geometry, rolling downhill, curving around hills. The ball is like a photon, an entity moving through geometry. The landscape itself is like space-time curvature, the geometry through which things move. A deep valley in the landscape can trap balls that roll into it if the valley sides are steep enough and tall enough. The balls cannot escape because they lack the kinetic energy to climb back out. But the valley itself, the geometric depression, extends beyond its lowest point. The slopes exist wherever the landscape rises toward the surrounding high ground. The valley doesn't need to escape from itself because it's not an object in the landscape. It is the landscape's shape. Black holes work the same way in space-time rather than space. The event horizon marks the deepest part of the gravitational well, where the geometry becomes so extreme that even light cannot escape. But the space-time curvature extends smoothly beyond the horizon, becoming progressively gentler with distance. Stars and planets orbiting far from the black hole respond to the curvature in their local region, following geodesics through geometry that happens to be curved by the black hole's mass. But here's where the geometric picture creates a subtle problem. If gravity is just space-time curvature and that curvature was established when the black hole formed, what happens when the black hole moves? How does the curvature pattern update if gravity cannot transmit information from inside the horizon? This question brings us to gravitational radiation, the dynamic aspect of space-time geometry. While static curvature doesn't need to escape from anywhere, changes in curvature propagate through space-time as gravitational waves. These waves travel at exactly light speed, carrying energy and momentum, representing actual ripples in the geometry itself. When two black holes orbit each other, the time-varying curvature pattern produces gravitational waves that carry energy away from the system, causing the orbits to decay. Dr. Rainer Weiss, who shared the 2017 Nobel Prize for LIGO's detection of gravitational waves, emphasizes that these waves are not signals sent by the black holes. They're changes in space-time geometry propagating outward from the region where massive objects are accelerating. The waves exist in the space-time outside the event horizons. They're generated by the motion of mass energy, and that motion creates changing curvature patterns that propagate outward at light speed. The key insight is that gravitational waves, like static curvature, are properties of spacetime itself, not signals traveling through spacetime. When LIGO detects a gravitational wave, it's detecting the passage of a region of compressed and stretched spacetime. The wave is literally a traveling distortion in geometry. The black holes that created the wave did so through their motion outside each other's event horizons, creating time-varying curvature in the external spacetime that propagated away as waves. You might wonder whether gravitational waves can escape from inside an event horizon. The answer is no, for exactly the same reason light cannot escape. Gravitational waves, despite being geometry rather than particles, travel at light speed. Inside an event horizon, all light speed trajectories point inward. A gravitational wave generated inside the horizon propagates inward toward the singularity, never reaching the outside universe. The event horizon is a boundary for anything that travels at or below light speed, whether particles, light, or gravitational waves. So light is trapped by geometry that eliminates outward paths, while gravity exists as that geometry itself and was already present outside before the horizon formed. But this raises a quantum question. If gravity is geometry, how does it relate to the other forces which are transmitted by particles? Chapter 5. Force versus geometry. The distinction between gravity as geometry and other forces as particle interactions represents one of the deepest divides in modern physics. While electromagnetism, the strong nuclear force, and the weak nuclear force are all successfully described by quantum field theories involving force-carrying particles, gravity remains geometrical, described by Einstein's classical field equations. This divide creates profound problems for unifying physics. Let's establish how the other forces work. Electromagnetism, the force between charged particles, is mediated by photons. When an electron repels another electron, quantum field theory describes this as the continuous exchange of virtual photons between the electrons. These virtual photons are not directly observable, but their effects create the electromagnetic force. The photons carry momentum and energy between the charges, creating attraction or repulsion. The strong nuclear force, which binds quarks into protons and neutrons, is mediated by particles called gluons. These massless particles carry the color charge that quarks possess. Gluons are exchanged between quarks, creating the incredibly strong force that prevents quarks from being separated. The strong force becomes stronger with distance, unlike gravity or electromagnetism, which weaken with distance. This property, called confinement, ensures that individual quarks never appear in isolation. The weak nuclear force, responsible for certain types of radioactive decay, is mediated by W and Z bosons. These particles are massive, unlike photons and gluons, which is why the weak force has very short range. The W and Z bosons were discovered at CERN in 1983, confirming the electroweak theory that unifies electromagnetism and the weak force into a single framework at high energies. All three of these forces share a common structure in quantum field theory. They're described by gauge theories, mathematical frameworks where forces arise from local symmetries of the quantum fields. The force-carrying particles, called gauge bosons, are excitations of these fields. When particles interact electromagnetically, strongly or weakly, they're exchanging these gauge bosons, which carry force and momentum between them. Dr. Frank Wilczek, who won the 2004 Nobel Prize for work on the strong force, describes gauge theories as the most successful framework in physics. They make predictions that have been tested to extraordinary precision. The magnetic moment of the electron, for example, has been calculated using quantum electrodynamics to 12 decimal places and matches experimental measurements perfectly. Gauge theories work spectacularly well for 3 of the 4 fundamental forces. But gravity doesn't fit this framework. In general relativity, gravity is not a force mediated by particle exchange. It's space-time curvature, a geometric property, rather than a force field. Objects don't interact gravitationally by exchanging particles. They follow geodesics through curved geometry. This difference is not merely conceptual, it reflects fundamentally different mathematical structures underlying the theories. To put this in perspective using an analogy that highlights the conceptual divide, imagine you're playing two different video games. In one game, characters interact by shooting projectiles at each other. The projectiles carry energy and momentum, creating forces when they hit. This is like gauge forces mediated by particle exchange. In the other game, characters move on a curved landscape, following the terrain. Hills and valleys guide their motion without any projectiles being exchanged. This is like gravity as geometry. The question that has puzzled physicists since the 1930s is whether gravity can be reformulated as a gauge theory with a force-carrying particle, or whether its geometric nature is fundamental and irreducible. The hypothetical particle that would mediate gravity is called the graviton, a massless spin-2 particle that would be exchanged between masses to create gravitational attraction. Many physicists have attempted to develop quantum theories of gravity where gravitons play the role analogous to photons in electromagnetism. In such theories, when Earth orbits the Sun, the interaction would be described as continuous exchange of gravitons between the Sun and Earth, carrying momentum and creating the attractive force. The curvature of spacetime would emerge as a collective effect of countless graviton exchanges, similar to how electromagnetic fields emerge from photon exchange. But these attempts face severe difficulties. When you try to calculate gravitational interactions using quantum field theory techniques, the mathematics produces infinite results that cannot be removed through standard renormalization procedures that work for other forces. The theory becomes non-renormalizable, meaning it makes predictions that diverge to infinity and cannot be made finite through any consistent mathematical procedure. This suggests that quantum field theory, in its standard form, cannot accommodate gravity. Dr. Steven Weinberg, who won the 1979 Nobel Prize for unifying electromagnetism and the weak force, spent decades trying to construct a consistent quantum theory of gravity. He concluded that gravity's geometric nature might be fundamental, that trying to fit it into the gauge theory framework might be forcing it into an inappropriate mathematical structure. Gravity might require a completely different quantization approach. The 2016 detection of gravitational waves added experimental urgency to this question. LIGO observed ripples in spacetime produced by merging black holes, confirming that spacetime is indeed a dynamic, wave-supporting medium, not a static background. If spacetime can wave, quantum theory suggests it should also fluctuate at small scales, creating quantum foam where geometry itself becomes probabilistic and uncertain. But we have no consistent theory describing these quantum gravitational effects. Consider what happens at the event horizon from a quantum perspective. In quantum field theory, the vacuum is not empty, but filled with virtual particle pairs that briefly appear and disappear, borrowing energy from the vacuum for times short enough to satisfy Heisenberg's uncertainty principle. Near an event horizon, these virtual pairs can be separated, with one particle falling into the hole and the other escaping. This process, predicted by Stephen Hawking in 1974, causes black holes to radiate energy and slowly evaporate. Hawking radiation demonstrates that quantum effects near event horizons create real physical consequences, linking quantum mechanics, gravity, and thermodynamics in a single phenomenon. The radiation has a thermal spectrum, meaning the black hole has a temperature inversely proportional to its mass. Stellar mass black holes have temperatures far below the cosmic microwave background and absorb more energy than they radiate, growing slowly. But tiny black holes, if they exist, would radiate intensely, evaporating in bursts of high-energy particles. Dr. Hawking's calculation reveals a profound puzzle. If black holes evaporate completely, what happens to the information about the matter that fell in? Quantum mechanics requires that information is conserved, that knowing the complete quantum state of a system at one time allows you to calculate its state at any other time, but if information falls into a black hole, then the hole evaporates into thermal radiation carrying no information. The information appears to be destroyed, violating quantum mechanics. This information paradox has driven theoretical physics for 50 years. Does information escape somehow, encoded in subtle correlations in the Hawking radiation? Does it remain inside the evaporating hole until the very end, then emerge in the final burst? Does the paradox reveal that event horizons don't actually exist, replaced by some quantum structure that allows information to escape? Or does quantum mechanics itself fail in extreme gravitational environments? To put this in terms that capture the severity of the conflict, imagine you have two fundamental laws of physics. One says A must always happen, the other says A can never happen. Both laws have been tested extensively in their respective domains and always proven correct, but black holes create a situation where both laws simultaneously apply, creating a direct contradiction. That's the current state of quantum gravity. We have two extraordinarily successful theories, quantum mechanics and general relativity, that make contradictory predictions in extreme situations. The event horizon crystallizes this conflict. In general relativity, the horizon is a smooth surface where nothing special happens locally. An infalling observer crosses it without noticing anything dramatic. But quantum field theory suggests the horizon should be surrounded by a firewall of high-energy particles that would incinerate anything trying to cross. These predictions directly contradict each other. You might be thinking this seems like an abstract problem for theorists, irrelevant to understanding whether gravity escapes black holes. But the conflict is fundamental to the question. If gravity is truly geometric, as general relativity describes, then it doesn't need to escape because it's not inside the hole. But if gravity is mediated by gravitons, quantum particles exchange between masses, then those gravitons would need to escape from inside the horizon, which seems impossible. The nature of gravity and the behavior at horizons are intimately connected. Some theoretical approaches try to resolve this by suggesting that spacetime itself is not fundamental, but emergent from something more basic. In these theories, gravity arises as a collective phenomenon from underlying quantum degrees of freedom, similar to how temperature emerges from molecular motion. The event horizon might be an emergent feature that appears classical at large scales, but has quantum structure at small scales that allows information to escape. Dr. Juan Maldacena's 1997 discovery of the AD-S CFT correspondence provided one framework for understanding gravity as emergent. In this approach, a gravitational theory in a certain type of curved spacetime is mathematically equivalent to a quantum field theory without gravity living on the boundary of that spacetime. Gravity emerges from the quantum theory, suggesting it's not fundamental but a consequence of deeper quantum structure. So we have a profound divide: gravity as geometry versus forces as particle exchange, classical smoothness versus quantum discreteness, information conservation versus horizon thermodynamics. These conflicts suggest our understanding remains incomplete, but they don't change the answer to our original question. Gravity doesn't escape from black holes because it's not inside trying to get out. It's the curvature of space-time that was already present outside, established by the mass distribution, persisting as geometry regardless of what happens to matter inside the horizon. The quantum mysteries deepen the story but don't change the geometric answer. Whether gravity is ultimately geometric or mediated by gravitons, the classical description remains valid for macroscopic black holes. And in that description, gravity is curvature, not a signal that needs to escape. But this raises one final question. If gravity is curvature that doesn't escape and light is trapped by that curvature, what does this tell us about the nature of reality itself? Chapter 6. Space-time's primacy. The resolution to our paradox reveals something profound about the structure of reality. Space-time is not a stage where physics happens. Space-time is physics, the primary entity from which everything else emerges. Understanding this primacy transforms how we think about existence, causality, and the relationship between matter and geometry. Let's establish what we mean by space-time primacy. In pre-relativity physics, space and time were absolute, unchanging backgrounds against which events occurred. Space was an infinite, static, three-dimensional container. Time was a universal clock ticking forward uniformly everywhere. Matter and energy existed within this container, moving through space and evolving in time, but not affecting the structure of space or time themselves. Einstein shattered this picture twice. First, special relativity in 1905 showed that space and time are not separate, but woven into a single, four-dimensional space-time. Different observers moving at different velocities slice this four-dimensional structure differently, experiencing different separations of events into space and time. What one observer measures as purely spatial separation, another observer might measure as a combination of spatial and temporal separation. Space-time is fundamental. Space and time separately are observer-dependent. Then General Relativity in 1915 went further, showing that space-time is not a static background but a dynamic entity that curves and flexes in response to matter and energy. Mass tells space-time how to curve, and curved space-time tells mass how to move. Matter and geometry are locked in reciprocal influence, neither primary, both aspects of a unified description. Dr. John Wheeler, who coined the term black hole in 1967, summarized this with memorable poetry. Space-time tells matter how to move, matter tells space-time how to curve. This is not a metaphor, it's a precise description of Einstein's field equations, which relate space-time curvature at each point to the distribution of matter and energy at that point. The equations are local, meaning the geometry at a location depends only on the matter-energy at that location, plus boundary conditions that ensure consistency across the whole space-time. To put this in perspective using a specific example that reveals the reciprocal relationship, consider a star forming from a collapsing gas cloud. Initially, the gas is diffuse, creating weak space-time curvature. As gravity pulls the gas inward, the density increases, which increases space-time curvature, which strengthens gravity, which pulls the gas inward faster, creating a feedback loop. The geometry and the matter co-evolve, each influencing the other, until equilibrium is reached, when fusion pressure balances gravitational collapse. When the star eventually exhausts its fuel and collapses into a black hole, this co-evolution continues to its extreme conclusion. The matter compresses to infinite density at a singularity, creating infinite space-time curvature. The geometry becomes so extreme that it closes off a region of space-time from causal contact with the outside universe. The event horizon is the boundary of this closed region, defined purely by geometry, marking where space-time curvature reaches the critical level for light-speed escape velocity. But here's what's crucial: the singularity, where matter reaches infinite density, is not a place in space. It's a moment in time for anything that falls into the black hole. The event horizon, while it appears as a spherical surface in space from outside, is actually a surface in space-time, a three-dimensional boundary in four-dimensional space-time geometry. Crossing the horizon is moving forward in time just as much as moving inward in space. This space-time perspective resolves many apparent paradoxes. When someone asks, what happens to matter at the singularity, they're implicitly thinking of the singularity as a place that exists now, somewhere inside the black hole. But the singularity is not simultaneous with the present outside. It's in the future of anything that crosses the horizon. Asking what's happening at the singularity now is like asking what's happening tomorrow morning right now. The question contains a category error, mixing spatial and temporal concepts inappropriately. The 2022 image of Sagittarius A-Eats, the black hole at our galaxy's center, captured by the Event Horizon Telescope, shows the shadow cast by the event horizon as seen from our spacetime location. That shadow is a projection of four-dimensional spacetime geometry into our three-dimensional spatial view. We're seeing the effect of extreme spacetime curvature on light paths, observing geometry directly through its influence on electromagnetic radiation. Dr. Leah Medeiros, part of the EHT collaboration, describes the shadow as a photograph of spacetime curvature. The bright ring surrounding the shadow is emitted by hot gas orbiting the black hole at speeds approaching light speed. The light from this gas follows curved paths through warped spacetime before reaching Earth. The shadow region in the center corresponds to trajectories that cannot reach us because they curve too severely, either falling into the hole or orbiting in unstable paths before eventually falling in. Consider what this means for the nature of existence. Matter and energy are not things that exist in spacetime as separate entities. They are aspects of spacetime's geometry, concentrations and patterns in how spacetime curves. An electron is a localized excitation of quantum fields that curve spacetime in its vicinity. A photon is an electromagnetic wave propagating through spacetime, carrying energy that contributes to spacetime curvature. Everything we call stuff is really patterns and distortions in spacetime geometry. This perspective explains why gravity doesn't need to escape from black holes. Gravity is not something separate from spacetime that could be inside or outside a black hole. Gravity is spacetime curvature itself. The black hole is a region of spacetime with extreme curvature. That curvature extends continuously throughout spacetime, becoming gentler with distance from the hole's center. The event horizon marks where curvature reaches a critical level, but it's not a boundary for the curvature itself, which is smooth and continuous across it. To put this in terms that connect to observable phenomena, consider gravitational time dilation. Clocks run slower in stronger gravitational fields, meaning at lower spacetime locations. This is not because some force is acting on the clocks, slowing their mechanisms. It's because time itself flows at different rates at different spacetime locations, with the flow rate determined by local curvature. A clock near a black hole's event horizon runs extremely slowly compared to a clock far away, not because the clock is damaged, but because spacetime near the horizon has a different structure than spacetime far away. GPS satellites must account for this relativistic time dilation to provide accurate positioning. Satellite clocks at orbital altitude run about 45 microseconds per day, faster than ground clocks due to weaker gravitational field. If this effect weren't corrected, GPS positions would drift by about 10 kilometers per day, rendering the system useless. The correction works because we understand that spacetime curvature affects time flow, and we can calculate precisely how much effect different curvature levels have. Near a black hole, these effects become extreme. At the event horizon, time dilation becomes infinite from an external observer's perspective. A clock at the horizon appears frozen, its ticks stretched to infinite duration. But from the clock's own perspective, from the proper time measured by the clock itself, nothing special happens at the horizon. The clock continues ticking normally. It's only the relationship between time at the horizon and time far away that becomes singular. This demonstrates a crucial feature of spacetime. It's not globally uniform but locally diverse. Different regions have different geometric structures, different rates of time flow, different amounts of curvature. There's no universal now spanning all of spacetime. Each path through spacetime has its own proper time, measuring duration along that path, and different paths accumulate different amounts of proper time between the same two events. Dr. Carlo Rovelli, a theoretical physicist working on quantum gravity, argues that we should abandon the concept of global time entirely, thinking instead of space-time as a collection of events with causal relationships but no universal temporal ordering. In this view, asking what's happening right now inside a distant black hole is meaningless because right now is not defined for widely separated locations in curved spacetime. You might find this philosophical, but it has practical implications for understanding black holes. The event horizon is not happening right now in any absolute sense. It's a feature of space-time geometry that different observers at different locations will encounter at different proper times along their world lines. An observer falling into the black hole crosses the horizon at a specific point on their world line, experiencing a specific proper time duration from any reference event. But an external observer never sees this crossing, watching the infalling observer asymptotically approach the horizon over infinite external time. Both perspectives are valid. Both describe the same space-time geometry from different viewpoints. The geometry itself is the primary reality. The different descriptions from different observational perspectives are all representations of that single underlying geometric structure. This primacy of space-time resolves our original question completely. Gravity is not something that needs to escape from black holes because gravity is not a thing moving through space-time that could be trapped. Gravity is space-time curvature, a geometric property that exists wherever space-time exists, including both inside and outside event horizons. Light, conversely, is electromagnetic radiation moving through space-time, following geodesics determined by local curvature, and those geodesics lead only inward from inside horizons. The distinction is absolute: geometry versus content, structure versus information, framework versus entities within the framework. Black holes trap content while being defined by structure. They trap light, matter, energy, information, anything that moves through space-time. But they are themselves structure, space-time curved to its extreme limit, and structure cannot trap itself. So space-time is primary, geometry defines existence, and understanding this transforms the paradox into clarity. But this raises one final, unsettling question. If space-time itself can be curved, warped, even trapped in black holes, what does this mean for the ultimate nature of reality? Chapter 7, Reality's Fabric. Understanding. Space-time as the fundamental fabric of reality, more basic than matter or energy, forces us to confront questions about existence that physics alone cannot fully answer. If space-time is primary, what is space-time made of? Is it infinitely divisible, or does it have a smallest unit? Is it continuous or discrete? And most fundamentally, does it emerge from something even more basic? Or is it the bottom layer of reality? Let's start with what we know. General Relativity treats space-time as a smooth, continuous manifold, a four-dimensional surface that can be curved and flexed, but has no fundamental graininess or structure at small scales. In this description, you can zoom into any region of space-time and find more space-time, infinitely divisible, with no smallest unit or fundamental discreteness. Space-time is like the surface of a perfectly smooth sphere, curved but continuous. But quantum mechanics suggests everything has fundamental discreteness at small scales. Energy comes in discrete quanta. Angular momentum is quantized. Even space and time might be quantized, composed of discrete units, below which no further division is meaningful. The Planck length, approximately 10⁻⁵ meters, is often considered the scale at which quantum gravitational effects should become dominant, where the smooth space-time of general relativity breaks down into some kind of quantum foam. Dr. Lee Smolin, a theoretical physicist working on loop quantum gravity, has proposed that space-time is fundamentally discrete, composed of quantum units of space and time woven together into the appearance of continuous geometry at larger scales. In this view, zooming into space-time far enough would reveal a network of discrete connections, a quantum geometry underlying classical smoothness. Space would be made of space atoms, irreducible units that cannot be subdivided. To put this in perspective using an analogy that captures the continuous versus discrete question, consider a television screen viewed from different distances. From across a room, the image appears continuous and smooth. Move closer, and you begin to see individual pixels, discrete units arranged in a grid. Is space like the distant view truly continuous, or like the close-up view discrete at small scales but appearing continuous when viewed from our macroscopic perspective? The answer matters profoundly for understanding black holes. If space-time is truly continuous down to arbitrarily small scales, then the singularity at a black hole's center represents a genuine breakdown of physics, a point where density and curvature become infinite. But if space-time is discrete at Planck scales, then the singularity might be replaced by some quantum structure, a region of maximum but finite density where space-time is compressed to its minimal units but does not collapse to a true point. String theory, perhaps the most developed attempt at quantum gravity, proposes that fundamental entities are not point particles but tiny vibrating strings with different vibration modes corresponding to different particles. In this framework, space-time itself emerges from relationships between strings. The geometry we experience is not fundamental but emergent, arising from the quantum properties of underlying stringy structure. Gravity is transmitted by closed strings in a particular vibration mode, giving gravitons a fundamental description. Dr. Brian Greene, a string theorist at Columbia, describes space-time in string theory as a secondary concept derived from more primary quantum entities. If this is correct, then asking what space-time is made of is like asking what temperature is made of. Temperature is not made of anything, it's a collective property of molecular motion. Similarly, space-time might be a collective property of quantum information, or quantum entanglement, not a fundamental entity but an emergent one. The 2019 work by Leonard Susskind and others on the relationship between quantum entanglement and space-time geometry suggests that space-time connectivity might literally be quantum entanglement. In this radical view, when two regions of space are connected by smooth geometry, the quantum states in those regions are entangled. Space-time geometry emerges from patterns of entanglement in underlying quantum degrees of freedom. Cut the entanglement, and the geometry disconnects. Strengthen entanglement, and geometry becomes more tightly connected. This ER-EPR conjecture, named after Einstein-Rosen bridges wormholes and Einstein-Podolsky-Rosen entanglement, proposes that wormhole connections through space-time are equivalent to quantum entanglement through Hilbert space. A maximally entangled pair of quantum systems is connected by a non-traversable wormhole in space-time. This would make geometry and quantum entanglement two descriptions of the same underlying phenomenon. Consider what this means for black holes. An event horizon might not be a fundamental boundary, but an emergent feature arising from how quantum information is organized. The singularity might not be a geometric point, but a region where quantum information is maximally compressed. Hawking radiation might not be thermal radiation from a classical horizon, but quantum information slowly escaping from an entanglement structure that appears classical at macroscopic scales. To put this in terms that connect to physical observations, consider what we actually measure when we observe a black hole. We detect electromagnetic radiation from gas orbiting outside the horizon. We observe gravitational waves from merging holes. We image the shadow cast by the event horizon. All of these are properties of space-time outside and near the horizon. We never directly observe the interior, never measure the singularity, never probe the Planck scale structure, where quantum gravity becomes important. This observational limitation means our understanding of black hole interiors is theoretical rather than empirical. We have general relativity, which predicts singularities and smooth event horizons. We have quantum mechanics, which suggests these features should be modified at small scales. But we cannot test these predictions directly because the relevant scales are hidden behind event horizons, inaccessible to observation. The 2015 LIGO detection of gravitational waves from merging black holes provided our most detailed probe of black hole dynamics, confirming that the holes merge smoothly, producing a final black hole whose properties match general relativity's predictions precisely. The gravitational wave signal shows the in-spiral, merger, and ring-down phases, with the ring-down being the final black hole settling into a stable configuration, its event horizon oscillating like a struck bell before returning to perfect spherical symmetry. Dr. Alessandra Buonanno at the Max Planck Institute, who developed the waveform models used to interpret LIGO signals, emphasizes that these observations test general relativity in the strong field regime, where space-time curvature is extreme but still outside event horizons. We observe the geometry responding dynamically to the motion and merger of massive objects. We confirm that space-time behaves as Einstein predicted, carrying ripples that propagate at light speed, warping the fabric of reality itself. But the observations don't tell us what space-time fundamentally is. They confirm it behaves as general relativity describes at the scales we can observe. Whether space-time is continuous or discrete, fundamental or emergent, composed of strings or loops or quantum information, remains open. The empirical success of general relativity is compatible with many different answers to these foundational questions. You might be wondering why we should care about the fundamental nature of space-time if general relativity works so well at observable scales. The answer is that understanding foundations matters for extending physics into new regimes. General relativity breaks down at singularities, predicting infinite densities and curvatures, which is almost certainly wrong. A complete theory should remain finite, describing what actually happens at the centers of black holes, rather than producing mathematical infinities that signal theory failure. Moreover, the quantum nature of spacetime affects black hole thermodynamics and information conservation. If Hawking radiation carries information, that information must be encoded in correlations between emitted quanta, and those correlations depend on the quantum structure of the horizon. Understanding black hole information requires understanding quantum spacetime, which requires knowing whether spacetime is discrete, emergent, or something else entirely. The various approaches to quantum gravity, string theory, loop quantum gravity, asymptotic safety, causal set theory, make different predictions about Planck scale spacetime structure. Some predict discreteness, others find continuity maintained. Some suggest spacetime has more than 4 dimensions at small scales. Others propose that time itself is emergent, not fundamental. These are not merely philosophical preferences, they're concrete physical proposals that could in principle be distinguished by observation if we could probe Planck scales. Consider what it means for your existence that spacetime might be emergent. You are patterns of matter and energy, particles following trajectories through spacetime, neural activity creating consciousness through organized complexity. If spacetime emerges from quantum information, then your existence is patterns in patterns, information about information, experiences arising from organization of underlying quantum degrees of freedom that themselves create the geometry you experience as space and time. This layered emergence doesn't make you less real. Temperature is emergent from molecular motion, but heat is genuinely felt. Solidity is emergent from electromagnetic forces between atoms, but walls are genuinely hard. Consciousness might be emergent from neural activity, but your experiences are genuinely felt. Emergence doesn't negate reality. It reveals that reality has hierarchical structure, with properties at one level arising from organization at deeper levels. Dr. Sean Carroll at Johns Hopkins has written extensively about emergence and fundamentality, arguing that we should be pluralistic about ontology, recognizing that objects and properties at different levels of description are all real in their own contexts. Tables exist as macroscopic objects even though they're composed of atoms. Space-time exists as continuous geometry even if it emerges from discrete quantum structure. Black holes exist as classical objects even though their interiors might have exotic quantum properties. To put this in terms that illuminate the practical implications Consider what happens when you fall toward a black hole. From your perspective, following your proper time, you approach the event horizon and cross it smoothly. General Relativity predicts you notice nothing special at the crossing, experiencing only tidal forces that stretch you vertically and compress you horizontally as you fall deeper into increasingly curved space-time. Eventually, these tidal forces grow infinite at the singularity, destroying you in a process called spaghettification. But if space-time is quantum at small scales, the singularity might be replaced by a region of extreme but finite curvature where quantum gravitational effects dominate. You might not be infinitely stretched, but rather encounter some quantum boundary where classical notions of trajectory and position break down. What happens then depends on the specific quantum gravity theory, and we don't yet know which theory is correct. The firewall paradox, proposed in 2012 by Ahmed Almheiri, Donald Maroff, Joseph Polchinski, and James Sully, suggests an even more dramatic possibility. If information is conserved in black hole evaporation, quantum mechanics requires strong entanglement between late Hawking radiation and early radiation, but the equivalence principle requires smooth geometry at the horizon, which implies different entanglement structure. These requirements seem incompatible, suggesting that either information is lost, or the equivalence principle fails, or something else dramatic occurs. One resolution proposes that quantum corrections to geometry create a firewall of high-energy particles at or near the event horizon. An infalling observer would be incinerated by this firewall rather than crossing smoothly. This would violate the equivalence principle, the idea that freely falling motion eliminates local gravitational effects, but it would preserve information conservation. The firewall debate remains unresolved, with different physicists advocating for different resolutions. Dr. Stephen Hawking, before his death in 2018, proposed that black holes don't have true event horizons, but rather apparent horizons, quantum surfaces that appear classical at large scales but have complex quantum structure that allows information to escape gradually. In this picture, the sharp boundary we call the event horizon is an approximation valid in classical gravity, but modified by quantum effects. The true quantum structure is fuzzy, not sharp, with information seeping out through quantum processes we don't yet fully understand. These debates might seem abstract, but they reveal something profound about the limits of current knowledge. We have two extraordinarily successful theories: General Relativity describing gravity and space-time geometry, and quantum mechanics describing the microscopic world. Both work perfectly in their respective domains, but at black hole horizons and singularities, both domains overlap, and the theories give contradictory answers. Consider what this means for understanding whether gravity escapes black holes. In classical general relativity, the answer is clear: gravity is geometry, not something that escapes. In quantum gravity, the answer might be more nuanced. If gravity is mediated by gravitons, quantum particles of spacetime curvature, then we need to understand whether gravitons can cross event horizons, whether the horizon is fundamentally sharp or quantum fuzzy, whether spacetime itself breaks down at small scales. But here's what remains true regardless of quantum corrections. At the macroscopic scales we observe, classical general relativity describes black holes accurately. The event horizons LIGO observes merging are classical objects behaving as Einstein predicted. The shadow imaged by the Event Horizon Telescope is a classical geometric effect. The gravitational influence of black holes on orbiting stars is classical spacetime curvature. Quantum gravity modifies small-scale structure and long-term evolution through Hawking radiation, but it doesn't change the basic classical picture at observable scales. You might be thinking, this leaves our original question partially unanswered if quantum gravity changes the story. But the quantum corrections don't change the fundamental answer. Whether gravity is classical geometry or mediated by quantum gravitons, it's still fundamentally different from light. Space-time structure, whether continuous or discrete, fundamental or emergent, extends throughout all of space. Light is energy moving through that structure, subject to being trapped by geometry. The distinction remains regardless of whether we describe it classically or quantum mechanically. So space-time is the fundamental fabric, possibly emergent from quantum degrees of freedom, possibly discrete at Planck scales, definitely primary to matter and energy. Gravity is this fabric's curvature, not something traveling through it. Light is energy propagating through the fabric, subject to its geometry. Black holes are regions where the fabric curves so extremely that it traps everything except its own geometric structure. But this complete answer raises one final conceptual question. If we understand all this, why does the paradox feel so compelling? Why does it seem like gravity should be trapped if light is? Chapter 8. Intuition's failure. The reason, if light cannot escape, how can gravity, feels like a paradox, is that human intuition is calibrated for everyday physics, not relativistic space-time geometry. Our brains evolved to navigate Newtonian environments where gravity is a force, space and time are separate, and the speed of light seems instantaneous. These intuitions serve us well in daily life, but break down completely when confronting black holes. Let's examine where intuition comes from and why it fails. Every human brain builds models of physics through experience. You learn as an infant that dropped objects fall downward, that pushing harder produces more motion, that things don't spontaneously appear or disappear. These learned patterns become intuitions, automatic expectations about how the world works that feel obvious and self-evident. But these intuitions are really just models calibrated to Earth's surface, where gravity is weak and uniform, velocities are tiny fractions of light speed, and quantum effects are imperceptible. Your intuition has never experienced space-time curvature dramatic enough to trap light. It has never encountered objects moving at relativistic speeds where time dilation becomes significant. It has never seen quantum superposition or entanglement. So when you try to reason about black holes using intuition, you're applying tools calibrated for completely different regimes of physics. Dr. Daniel Kahneman, who won the Nobel Prize in 2002 for work on judgment and decision-making, distinguishes between two types of thinking: fast, automatic, intuitive thinking, and slow, deliberate, analytical thinking. Intuition is fast thinking, pattern matching based on past experience. It works brilliantly for familiar situations but fails systematically when confronting novel situations that do not match past patterns. Black holes are as novel as situations get. To put this in perspective, using a specific example of intuitive failure, consider simultaneity. Your intuition tells you that now is universal, that when you experience this moment, there's a corresponding now everywhere in the universe. If someone is reading on Mars, they're reading now at the same moment you're watching this video. This seems obviously true, impossible to doubt. But special relativity proves it's false. Simultaneity is relative to reference frame. Events that are simultaneous in your reference frame are not simultaneous in a moving frame. There is no universal now spanning the cosmos. Your intuition is simply wrong about this, misled by the fact that at everyday velocities, the relativistic corrections are too small to notice. Your brain never learned to correct for relativity because it never needed to. The same failure occurs with gravity. Your intuition treats gravity as a force, something pulling objects together, because that's how Newton described it, and that description works perfectly well for everyday experience. You've never seen orbits curve through space-time without a force. You've never experienced falling as moving along a straight geodesic through curved geometry. So when you hear gravity is space-time curvature, not a force, your intuition rebels, insisting that of course gravity is a force. You can feel it pulling you downward right now. But what you feel is not gravity pulling you down, it's the ground pushing you up, preventing you from following the geodesic you would naturally follow in curved spacetime. When you're standing, you're accelerating upward at 9.8 meters per second squared relative to the freely falling frame. The force you feel is not gravity, it's the electromagnetic forces in the floor's atoms pushing against the electromagnetic forces in your feet, preventing you from falling freely. Gravity is the curvature that makes free fall the natural motion. The force is what prevents free fall, not what causes it. This inversion of the intuitive picture is disorienting. It feels wrong even when you intellectually understand it's correct. Your brain keeps trying to revert to the Newtonian picture where gravity is a downward force and standing still is the natural state. Overcoming this requires conscious effort, deliberately applying the correct geometric picture, even though it feels unnatural. Dr. Lisa Randall at Harvard, who works on extra dimensions and particle physics, describes teaching general relativity as rewiring students' brains. The mathematics is challenging but learnable. The conceptual rewiring, replacing force-based intuitions with geometric ones, is harder. Students can calculate geodesics perfectly while still intuitively thinking of gravity as a pulling force. The intuition persists even after the mathematics is mastered. Consider another intuitive failure, the idea that black holes are cosmic vacuum cleaners sucking in everything nearby. This image appears constantly in popular media, depicting black holes as hungry monsters devouring stars and gas indiscriminately. The reality is far more mundane. A black hole's gravitational influence is exactly the same as any other object of equivalent mass. If the Sun suddenly became a black hole of equal mass, Earth's orbit would not change at all. We would continue orbiting at the same distance and speed, though we'd freeze without sunlight. Black holes only trap material that crosses the event horizon. Everything outside the horizon can orbit stably, just as planets orbit stars. The dramatic accretion disks and jets seen around some black holes result from gas falling in from close distances, where tidal forces and friction heat the gas to millions of degrees, causing it to radiate intensely. But this is not the black hole sucking material in. It's material following geodesics through curved space-time that happen to lead inside the horizon, releasing gravitational potential energy as radiation in the process. Your intuition expects dramatic activity because black holes sound dramatic. But most black holes are quiescent, orbited at safe distances by stars and gas that will never fall in, creating no more danger than any other massive object. The danger is crossing the event horizon, and that requires getting very close, closer than you'd need to get to any ordinary star to be destroyed by tidal forces. Black holes are not cosmic threats, they're just very compact, massive objects with event horizons. To put this in terms that reveal another intuitive failure, consider the question, what happens to time inside a black hole? Your intuition imagines time as a universal river flowing forward, and you wonder whether it flows differently, faster, or slower inside the horizon. But time is not a universal river. It's a dimension of space-time, and its structure depends on local geometry. Inside a horizon, the time-like direction points toward the singularity. Time flows forward, but forward in time means toward the singularity. This is not slower or faster time. It's different directional structure of time. The question, how fast does time flow inside, misapplies intuitions from external space-time to a region with completely different geometric structure. It's like asking how north is down. The question mixes incompatible concepts. Once you cross the horizon, the categories change. Radial direction becomes time-like, time becomes space-like. Asking about time flow in familiar terms doesn't work because the framework has shifted. The difficulty of abandoning intuition is not weakness or ignorance, it's a consequence of how brains work. Evolution optimized human cognition for survival in specific environments, not for understanding relativistic space-time geometry. The fact that we can understand it at all, despite our intuitions pulling us toward Newtonian thinking, is remarkable. We override intuition with mathematics, using equations to guide us through conceptual territory where intuition cannot follow. Dr. Richard Feynman, one of the great physics pedagogues of the 20th century, advised students to shut up and calculate when intuition fails. Learn the mathematics, trust the equations, and let your intuition catch up gradually through repeated exposure. Eventually, after enough calculation and contemplation, the geometric picture starts feeling more natural. You begin to intuitively see space-time curvature rather than forces, geodesics rather than pulls. But this takes time and effort. The initial intuitions never disappear completely, they're just overlaid with better models that take precedence. Consider what this means for understanding our central question. Your intuition wants gravity to be something emitted or transmitted from inside the black hole, something that must escape to affect the outside. This intuition is wrong, but predictably wrong given how brains work. The correct understanding requires abandoning the emission picture entirely, replacing it with the geometric picture where gravity is curvature of the space-time fabric itself, not something traveling through that fabric. You might have noticed that every resolution in this video requires replacing intuitive concepts with geometric ones. Force becomes curvature. Gravity becomes geometry. The event horizon becomes a geometric surface rather than a physical barrier. Time becomes a dimension rather than a universal flow. All of these replacements violate intuition because intuition is built on Newtonian foundations. Einstein's revolution was not just new equations, it was a complete reconceptualization of what space, time, and gravity are. The persistence of the paradox in people's minds, despite clear explanations available for over a century, demonstrates how powerful intuitive physics is. Even people who understand the mathematics often retain intuitive pictures that contradict the math. The brain maintains parallel models, a correct geometric model used for calculation, and an incorrect force-based model used for intuitive visualization. Recognizing this duality is important. You cannot eliminate the intuitive model. You can only learn to recognize when it's misleading and deliberately activate the correct geometric model instead. So intuition fails because it's calibrated for Newtonian physics in everyday environments, not for relativistic extremes where space-time itself becomes the primary entity. The paradox persists because abandoning intuition is difficult, requiring conscious effort to apply geometric thinking even when it feels unnatural. But the effort is worthwhile because it reveals reality's actual structure rather than our evolved approximation of it. But this raises one final question. If even educated people struggle with this, if intuition so strongly resists the correct picture, how do we effectively communicate these ideas? How do we help others overcome their intuitive barriers? Chapter 9. Teaching Geometry. Effectively, communicating relativistic concepts requires meeting people where they are, acknowledging their intuitions while gently guiding them toward better models. The challenge is pedagogical, not intellectual. People are perfectly capable of understanding space-time geometry. They just need the right conceptual bridges from familiar physics to relativistic physics. Let's examine what makes relativistic concepts difficult to teach. The primary obstacle is that everyday experience provides no direct evidence of space-time curvature. You've never seen light curve through empty space. You've never observed time dilation from moving at relativistic speeds. You've never measured length contraction. All the signatures of relativity are either too small to detect without precise instruments or occur in extreme environments far from daily life. Teaching relativity means teaching about a world you've never directly experienced. This is fundamentally different from teaching classical physics. When teaching about forces, you can demonstrate with pushes and pulls students feel directly. When teaching about motion, you can throw balls and watch trajectories students see with their own eyes. When teaching about energy, you can show transformations between forms that students experience as heat, or motion, or sound. The phenomena are directly accessible to intuition. But when teaching general relativity, you cannot show space-time curvature directly. You cannot demonstrate an event horizon. You cannot let students fall into a black hole and report back. All you have are mathematical descriptions, indirect evidence from distant astronomical objects, and metaphors that capture some aspects while misleading about others. Teaching requires building new intuitions from scratch using only indirect evidence and mathematical logic. Dr. Edwin Taylor and John Archibald Wheeler developed one influential pedagogical approach in their textbook, Exploring Black Holes. They used geometric methods, space-time diagrams, and the concept of proper time to build intuition about relativistic physics without requiring advanced mathematics. Students learn to visualize world lines through space-time, to see curvature geometrically, to understand time dilation as different path lengths through space-time rather than mysterious clock slowing. To put this in perspective using a specific teaching challenge, consider explaining why nothing can escape from inside an event horizon. The naive explanation, "gravity is too strong," reinforces force-based thinking and obscures the geometric reality. A better explanation uses the light cone picture, draws space-time diagrams showing how light cones tilt increasingly inward as you approach the horizon, until at and inside the horizon, all future-directed paths point inward. This geometric visualization reveals why escape is impossible without invoking forces. But even this requires students to understand space-time diagrams, light cones, future-directed paths, and the distinction between spatial and temporal directions. These are not intuitive concepts. They require careful introduction, practice with simple examples in flat space-time, then gradual extension to curved space-time near massive objects. The pedagogical sequence matters enormously. Introduce concepts in the wrong order and students become confused and frustrated. The rubber sheet metaphor, despite its limitations, remains valuable for initial conceptual bridging. It correctly conveys that mass curves space, that objects follow paths through curved geometry, and that sufficiently steep curvature can trap things. But it misleads in other ways. It shows only two-dimensional space, suggests space is embedded in higher dimensional space, and relies on ordinary gravity to make the sheet sag, using gravity to explain gravity. Teachers must use the metaphor while explicitly noting its limitations. Dr. Clifford Will at the University of Florida, who has written extensively about testing general relativity, emphasizes the importance of connecting theory to observations. Students often find relativity too abstract, too disconnected from reality. Showing them GPS time corrections, gravitational lensing images, gravitational wave detections, and black hole shadows grounds the theory in observable phenomena. The mathematics describes real effects we can measure, not just abstract speculation. Consider how to explain our central question. If light cannot escape, how can gravity to someone encountering it for the first time? The pedagogical sequence might be: first, establish that gravity is curvature, not force. Use the rubber sheet or similar metaphor. Emphasize that objects follow straight lines through curved space, that what appears curved from outside is straight from the object's perspective. Second, distinguish between things moving through space-time and space-time itself. Light moves through space. Gravity is the shape of space. Things moving through space can be trapped by sufficiently extreme curvature. The curvature itself is not moving through space, so it cannot be trapped by itself. Third, explain the event horizon as a geometric feature, a location where escape velocity equals light speed, defined by space-time curvature reaching a critical value. The horizon is not a physical barrier, it's where the geometry changes character, where all future paths point inward. Fourth, address the specific question: gravity doesn't need to escape because it was already outside before the horizon formed. The space-time curvature extends throughout space, established by the mass distribution. The horizon is a boundary for things trying to move from inside to outside, not for the curvature pattern itself. This sequence builds from intuitive concepts toward accurate geometric understanding, explicitly noting where intuition needs correction. Each step establishes conceptual foundation for the next. By the end, students have the tools to understand not just the specific answer, but the general principle that geometry and content are fundamentally different categories. To put this in terms of common misconceptions to address, many students think gravity is a pulling force emanating from masses. Event horizons are physical surfaces or membranes. Black holes actively suck in nearby material. Time stops at event horizons. Singularities are places inside black holes. Gravity must be transmitted by something traveling from inside to outside. Each misconception requires specific correction, showing not just that it's wrong, but why the correct picture is different and why the misconception arose. The pulling force misconception comes from Newton's successful description. The physical surface misconception comes from the word horizon, suggesting a boundary. The vacuum cleaner misconception comes from sensationalized media. Addressing misconceptions requires understanding their origins. Dr. Eric Mazur at Harvard developed peer instruction methods where students discuss conceptual questions in groups before answering. This works well for relativity because articulating your understanding to peers reveals gaps and confusions. When one student explains light cones to another, both benefit. The explainer by clarifying their own thinking, the listener by hearing peer-level language. The teacher becomes facilitator rather than sole source of knowledge. The challenge intensifies when moving beyond qualitative understanding to quantitative calculation. Students can visualize space-time curvature qualitatively, but struggle with the mathematics of curved geometry, tensor calculus, covariant derivatives, the Einstein field equations. These mathematical tools are essential for precise predictions, but present enormous pedagogical barriers. One approach introduces curved space-time through analogy with curved surfaces students already understand. A sphere's surface is two-dimensional but curved, demonstrating that curvature doesn't require embedding in higher dimensions. Geodesics on a sphere are great circles, the straightest possible paths given the geometry. This builds intuition for four-dimensional space-time curvature by analogy with two-dimensional spatial curvature. But analogies only go so far. Eventually, students must engage with the actual mathematics if they want deep understanding. This requires comfort with vectors, matrices, and calculus, then extension to tensor notation and curved space operations. The mathematical barrier is significant, restricting full understanding to students with substantial mathematical preparation. Consider what this means for public communication of relativity. Most people lack the mathematical background for full understanding, so communication must rely on qualitative descriptions, metaphors, and visualizations. This creates inevitable distortion. The geometric picture cannot be fully conveyed without mathematics. All qualitative descriptions simplify and mislead in various ways. The challenge is choosing simplifications that illuminate rather than obscure. The Event Horizon Telescope images of black holes provide powerful pedagogical tools precisely because they're actual photographs, not illustrations or simulations. When students see the real shadow of M87's black hole, they're seeing direct evidence of space-time curvature so extreme it traps light. The image makes the abstract concrete, transforming theoretical predictions into observable reality. This grounds the mathematical descriptions in physical phenomena students can see. You might be wondering whether it's worth the effort to develop accurate geometric intuition when Newtonian thinking works fine for everyday life. The answer depends on goals. If you only need to predict everyday phenomena, Newtonian physics suffices. But if you want to understand the universe's actual structure, how gravity really works, what black holes truly are, then the geometric picture is essential. It's not just more accurate. It reveals reality's actual architecture, rather than an approximation that happens to work locally. Teaching relativity is ultimately about expanding conceptual horizons, showing students that reality is stranger and more beautiful than everyday experience suggests. The universe is not built on intuitive foundations. It's built on geometric foundations that require mathematical language to describe precisely. Learning this language is difficult but rewarding, opening understanding of phenomena that would remain mysterious forever under Newtonian thinking. So effective teaching requires careful pedagogical sequences, explicit attention to misconceptions, connection to observations, and gradual building of geometric intuition. But even perfect teaching cannot eliminate the initial strangeness of relativistic concepts. Some conceptual difficulty is inherent because we're describing physics fundamentally different from everyday experience. But this raises one final question. Given all this difficulty, given how counterintuitive relativity is, why should anyone care? What does understanding that gravity is geometry rather than force actually matter for? Throughout this journey, we've discovered that gravity is space-time curvature rather than a force, that this geometric nature explains why it extends beyond event horizons while light is trapped, and that understanding this distinction reveals reality's actual structure beneath intuitive appearances. We've learned that event horizons are geometric features where space-time curvature reaches critical levels, making escape impossible not through force, but through geometry eliminating outward paths. We've explored how this conflicts with quantum mechanics, suggesting that space-time might be emergent from deeper quantum structure, and how our intuitions fail because they're calibrated for Newtonian environments rather than relativistic extremes. But perhaps the most profound insight is this: the universe is not built on the intuitive foundations of everyday experience. It's built on geometric foundations that require mathematical language to describe and conscious effort to comprehend. The question, if light cannot escape a black hole, how can gravity, arose from treating gravity and light as similar phenomena, both needing to propagate from inside to outside. The answer reveals they're fundamentally different. Light is energy moving through space-time, following geodesics that can be closed by extreme curvature. Gravity is space-time curvature itself, a geometric property that exists wherever space-time exists, requiring no propagation because it's not moving through space but is space's shape. This distinction between geometry and content, between the fabric of reality and things moving through that fabric, represents one of Einstein's deepest insights. Before general relativity, physics treated space and time as fixed backgrounds, unchanging stages where matter and forces interacted. Einstein revealed that space-time itself is a dynamical entity, curved by mass energy, with that curvature determining how objects move. The stage became an actor in the cosmic drama, not merely a passive container, but an active participant in physical processes. Black holes crystallize this insight by pushing space-time curvature to its extreme limit. At an event horizon, curvature becomes so severe that the future direction of time itself points inward. Everything inside, photons, particles, information, anything that exists within space-time, falls inexorably toward the singularity, not because forces pull it, but because forward motion in time means motion toward the singularity. The geometry has reached a configuration where escape is not difficult, but geometrically impossible, eliminated as a possibility by the structure of space-time itself. As you go about your day after watching this, remember that you're not standing still on a static Earth. You're accelerating upward through curved space-time at 9.8 meters per second squared, prevented from following your natural geodesic by electromagnetic forces in the ground pushing against your feet. When you see objects fall, remember they're not being pulled downward by a force. They're following straight lines through geometry curved by Earth's mass. and those straight lines through curved space appear as parabolic arcs from your accelerated reference frame. When you hear about black holes in the news, remember that they're not cosmic vacuum cleaners or mysterious threats. They're regions where space-time curvature has crossed a threshold, creating event horizons beyond which causal contact becomes impossible. The gravity you experience from a black hole at safe distance is exactly the same as gravity from any other object of equivalent mass. Only by approaching within a few Schwarzschild radii does the extreme curvature create dangers absent around normal stars. You are not separate from space-time. You are a pattern within it, matter and energy organized into complex structures that generate consciousness, awareness of the geometric stage on which existence unfolds. Every atom in your body curves space-time minutely. Every thought in your mind represents energy flowing through neural structures, energy that contributes to space-time curvature. You are simultaneously experiencing space-time curvature as gravity and creating space-time curvature through your mass energy. The distinction between observer and observed dissolves at the fundamental level where everything is geometry. The universe revealed by General Relativity is stranger and more beautiful than the Newtonian cosmos that preceded it. Space and time are woven together into a unified fabric. This fabric curves in response to matter and energy. Curvature determines how things move. Motion of matter creates time-varying curvature that propagates as gravitational waves. Black holes form where curvature becomes so extreme it creates permanent boundaries in space-time. All of this follows from the simple principle that gravity is geometry, not force. We live in a brief, bright epoch of cosmic history when stars shine, when black holes are forming from stellar collapse and growing through accretion, when gravitational waves ripple through space-time from merging compact objects. Future civilizations billions of years from now will inhabit a quieter cosmos where most black holes have settled into stable configurations, where gravitational wave events become rare, where the universe has evolved toward its long-term fate of increasing entropy and isolation. We are privileged to witness cosmic dynamics in an active phase. But regardless of epoch, the fundamental nature of gravity remains the same. It is and always will be space-time curvature, the geometric property of the fabric of reality, not something traveling through that fabric that could be trapped or blocked or prevented from extending throughout all of space. This truth is independent of technological capability, observational access, or theoretical understanding. It's a feature of how reality is structured at the most fundamental level accessible to current physics. If you made it this far, you've spent nearly an hour contemplating one of physics' deepest questions, working to understand why gravity behaves differently than light at event horizons, learning to think geometrically rather than intuitively about space-time. Consider hitting subscribe and giving this video a thumbs up if you appreciate deep dives into physics that challenge intuition and reveal reality's actual structure. And check out my video on what happens inside a black hole, where we explore the journey past the event horizon toward the singularity. I think you'll find it fascinating given what we've covered here. The paradox of gravity escaping while light cannot arose from intuitive thinking calibrated for everyday physics. The resolution required abandoning those intuitions, embracing the geometric picture where gravity is not something escaping but space-time's shape, established by mass distribution and extending throughout all of space. This is not semantic wordplay or mathematical trickery. It's the actual structure of reality revealed by rigorous theory, confirmed by precise observation. You cannot visualize four-dimensional curved space-time geometry directly. Your brain evolved to navigate three-dimensional Euclidean space, not relativistic space-time. But you can understand it mathematically, learn to work with the equations, make predictions that observation confirms. You can develop geometric intuition that, while imperfect, guides thinking better than Newtonian, force-based intuition. You can recognize when intuition misleads and consciously apply the correct geometric framework. Understanding why gravity doesn't need to escape from black holes is understanding what gravity is, not a force trapped or liberated, but geometry present wherever space and time exist. This understanding connects you to reality's deep structure, revealing the universe's actual architecture beneath appearances. It's knowledge worth having for its own sake, independent of practical applications, because comprehending the cosmos is part of what makes consciousness valuable, what transforms mere existence into meaningful experience of reality.